All right, you ready for another exciting lesson of combined uncertainty? So imagine you're a carpenter or you're working in the trade specifically, and you keep on cutting pieces, right? And those pieces are to be joined together, right? End to end. You're putting flooring in, you're putting boards in. Every time you do that, some of the uncertainty keeps on adding up, right? Because every single board has some uncertainty, and you keep adding it up. Similarly, I'm thinking COVID vaccines, right? I don't know if you got your shot or not, but remember when you were, I was here at, what's that sportplex called here on the Garden City one? The big complex there. Yeah, yeah. Yeah, so I actually right, you see the nurses, right? They had that big vial, and they would take out of that, and you got your shot, right? So every time actually a nurse pokes into the vial and takes some out, the syringe has some uncertainty, right? The vial has some uncertainty, and every time you take out, there's a combined effect happening there. Okay, it keeps adding up. So that's what we're going to explore here. So far, each measurement has an uncertainty, right? So far. And by the way, margin of error is the same thing as uncertainty. It's just a different way of talking about it. This is due to the limitation of the measuring device, also known as a precision. So I'm reviewing that, okay? But what happens if you combine measurements, right? What about if you keep removing an amount from a larger batch, right? And here it is, the total or combined uncertainty. This is straight from the province. The total or combined uncertainty is the sum of all uncertainties present. That's very important right there. It's due to the fact that each time something is measured and added to a total, the uncertainties also increase. The margin of error increases because something is measured repeatedly, right? Something is measured repeatedly. It may seem insignificant in most sectors, but it is very important to consider in some industries. So for example, if you're part of a NASA team, you're launching something to space, or you're getting ready for a mission, right? The amount of oxygen, all of that, the amount of food that needs to go with, that is all has to be very precise, because when you're out there, it may actually come down to lives, right, that are at stake. So for example, a plane weighing all the items that is being loaded, all the items being loaded on a plane, right? The pilot needs to take into account that the actual loaded weight may vary significantly. And this is due to the combined, right? Due to the combined uncertainties again. So I would say that most of us have traveled at some point, right? And you bring your luggage, and you hope that it's not going to be overweight, right? So they weigh it, and then they send it down the belt, right? And it goes into the plane, right? So every time that the attendant weighs your baggage, there's some uncertainty. That scale has some limitation, right? And that keeps on combining. As the luggage fills the plane, right, the pilot needs to know that whatever was weighed and added may actually be more than what it says on the paper, right? So they account for that. They know that, right? A gas station needs to be aware that the amount of fuel remaining in the holding tanks may be higher or lower than expected, right? Every time someone draws fuel to gas up their cars, right, a measurement is actually taking. The pump is measuring how much is being pumped into the car, right? So each time the uncertainty increases, each time a car fuels, there's the uncertainty actually gets bigger and bigger. Okay. So let's explore this further practically on an example, right? So 3 pieces of fabric are being sewn together. Notice 3 pieces, right? There's the 3 pieces here. So there's multiple items involved. It says determine the precision and uncertainty for each piece. This is how I would suggest you do questions like these. Stack them like that, all three pieces, and let's come up with the precision and uncertainty. Do they all have the same precision, guys? Look at the numbers. They all have 0.1, right? So we can do this very quick. So we can just say 0.1, uncertainty is 0.05. The precision here is 0.1 uncertainties, but this will not always be the case. That's why I'm getting you ready to do this every time. They may have different precisions. What about the units of lyrics? Well, I'm not answering yet, so it's okay to not have them in this particular case. This is A. We actually did A right now. We stated the precision and uncertainty for each piece. You know what? I feel like this is going to bite me, so I am going to take 5 seconds and add centimeters everywhere. Just go C and squiggly line, right? That's all you need to do. Doctor's note. B, calculate the total length and the combined uncertainty. So watch this, guys. I put a line under. When you do these, the precision is irrelevant. We just want the combined length of sewing all three pieces together. It should tell you that we need to add the values, right? So let's add this up. Let's do some mental math. 4, 3, and 1 is 8, right? And then 5, 0, and 0, that's just 5. 6 and 3 is 9. Hey, mental math, right? And then let's just put a big plus or minus here. And we're going to add the uncertainties together. So can we do this? I think you're going to be all right if I do this. The precision was only necessary to come up with the uncertainties. So let's add this all up. Two ways of doing this, guys. What's one way? Adding it all up, right? 0.05 plus 0.05 plus 0.05. That's 0.15. Or what would be the fastest way of doing that? 0.05 times 3. If you sew together 50 pieces, right? It'd be a lot of work adding up 50 times, right? So you got to kind of use whatever works best for you in that scenario. Remember, we just did that on the AC, 50 pieces, right? I went 50 times the uncertainty, and then I got that. So this right here answers question B. There's the combined length and the combined uncertainty of all the pieces. Okay. Determine the shortest and longest possible combined lengths. This is going right back to yesterday, right? For C, the max is going to be 95.8 plus 0.15. And my minimum length is going to be 95.8 minus 0.15. And it's 95.95. How's that? Pure coincidence. And the bottom one, it's basically 80, right? 95.80 minus 15, that's 65, right? So this is the, after you sew these things together, it could be as long as this or as short as this, right? Potentially, it could be that it's bang on. But if we consider the uncertainty, it could be longer and shorter by this much. Same thing would have applied if you sew 5 pieces together, 7, doesn't matter. You do it the same way. Okay. This is combined uncertainty, guys. So I'll just do this in our notes. We add uncertainties, right? And that gives us this number right here. That's what we call the combined total uncertainty. And in this case, it made sense to add up the pieces because you're sewing them together, right? So you're getting a longer piece. But sometimes it'll be minus here, but it's always plus here, always. The uncertainties are always being added together, okay? The uncertainties always increase. One more, and that'll be probably it for today. And you need to turn your brain off, right? Turn it off. I hope you do the homework that I post because time is ticking, right? Time is ticking. Tomorrow is going to be a new concept, which is tolerance. That's it. After tolerance, nothing new, but you kind of need to be on board with what we're doing. Okay, Moses has a bucket of water. Yeah, 20.5 liters. He needs to draw some water for some plants using a smaller jug. So let's put, there's a big bucket with 20.5 liters in it. And then there's a smaller jug that holds 1.2 liters. Do they both have the same precision? Yeah, okay. Just keeping that in mind. Not always, but in this case, yes. If Junior draws 3 jugs from the bucket, so he uses a small one to take 3, right? He scoops in there 3 times to water plants, right? Determine how much water will be left in the bucket, including the uncertainty. Right? So we'll do this. I will do it the long way, okay? So hang in there with me. I'll say, okay, what happens here is the big bucket has a precision of 0.1 liters. Why are you doing the precision, Mr. Dirksen? Because I need the uncertainty, which is 0.05. There you go. And I'm drawing 3, right? 1.2. Precision is the same. The uncertainty is the same. Not always, but I did start with it. I know this is a long way. Some of you would have just multiplied the small jug times 3, and that's okay. You're allowed to do that. And because they all have the same uncertainty and precision, it's a lot faster. It makes sense that we subtract the liters, right? The 1.2, because we're drawing out. So now, watch what I'm going to do. I'm going to go 20.5 minus 3 times 1.2, right? I'm going to take away 3 times 1.2, which is 3.6, right? That leaves me with 16.9 liters. That's how much is left. What are we going to put in between? Plus or minus. So this is basically ignored after. Unless I ask you for the precision and uncertainty, which most of the time I will not with these types of questions. And how many 0.05s are there? 4, right? I always add them. No matter what happens here. So times 4. So it's 0.2. Add uncertainties. Exclamation mark, highlight. And there you answer A. This is it. This right here is what this question was asking. How much is left with the total uncertainty, okay? What's the maximum minimum amount left in the bucket? I'm just going to go from here. Max min. 16.7 liters or 17.1 liters. This is for B, right? This answer is B right there. If Junior needs 17.5 liters to water, that doesn't sound right. To water a tree. That's what it's supposed to say. To water a tree. Will you have enough? You think he'll have enough? The maximum possible left in that bucket is this. So no. Even though it may seem silly to you, it's like, really? Just take whatever's left and dump it at the tree, right? That's what you would do, and that's what I would do. But in this particular case, since the maximum amount remaining is 17.1 liters, he will not have enough water. That's it. Before you go today, I know you're like, try the box question that I have right underneath. They all have different precisions, different uncertainties, so I kind of like mix it up on you. It'll probably take you 5 minutes, right, to do this. Do you need to beef up your study sheet? Maybe you need to do that, right? So I will post after today. Let me see. Write this down, okay? 26 to 31. Okay. All right, I'm going to do the box yet. I'm going to add it to the lesson. Let's see here. So the UPS store has received 3 packages from various customers. Calculate the total weight of all boxes and the combined uncertainty, right? So I don't know, maybe we can just do that right here. Right? The precision here is 0.1 kilogram. The uncertainty is 0.05. Maybe that's be too time consuming to do it twice, so I'll just take this back. Sorry about that. I want you to not have to do too much work, right? So I'm just going to stack this, right? Stack the boxes, what I did there. Right, so we take this box, we take that other box, and it's very important to say to not add anything that isn't there. So it's 2 kilograms, and then the third box is 1.45 kilograms. So right off the top, you can tell that they all have different precisions, which means they will all have different uncertainties, right? So we can say that, right, the precision is 0.1 of a kilogram. The uncertainty is plus or minus 0.05 of a kilogram. This one has a precision of what? 1 kilogram, okay? 1 kilogram. So the uncertainty would be plus or minus 0.5, half of a kilogram, right? Precision here is 0.01 kilogram, right? 0.01, and the uncertainty is 0.005 of a kilogram. So you can tell that it's all over the place, right? Got 2 decimals, 1 and 3. So the combined weight, obviously, the total combined weight is indicating that we need to add these, right? And for sure, we'll always add our uncertainty. So that's not even the question, right? I'm going to scratch the precision because we only needed it to get our uncertainty. So if you add this up, 2 and 1, that's 3.45. So that'll be 19.95 kilograms if you add this all up. Plus or minus, you just add all these up. And if you do, you will find that it adds up to this. Right? That's the combined uncertainty. So that would be the downside of actually having different scales, right? So now the uncertainties are all different, right? And especially if your precision is high, right? A kilogram, this thing can only go a kilogram at a time. So it also affects your uncertainty greatly, right? So what is the maximum and minimum combined weight of all boxes? Right, so the max possible weight would be 1995 plus 0.555. We'll answer that. And the min is 19.95 minus 0.555. So here we go. I'm going to use my calculator just to make sure I get it right. So that would be 13, watch this, right? Not 13, 19.395 kilograms. And I'm just going to add, sorry, and this is 20.505 here, okay? So we have our min and our max combined weight. So it's kind of weird, right, that way, but that's how we treat it, right? And so if this would be irrelevant at this point because we all know that a truck can handle this no problem, but if a truck had like a weight capacity, a weight limit, I'm thinking now in the spring, there's usually a weight limit on roads, right? So when they keep on adding weights, right, adding up weights, as they load the trucks, they need to make sure they don't surpass it. So the fact that there's a bunch of uncertainties that are adding up, right? Whoever loads the truck needs to take that into account because, right, even though it's 19.95 in this case, it could be, I did this wrong, sorry. Probably laughing right now. Anyways, 1995. I noticed that my max is smaller. This is, I have it backwards. Sorry. I'm going to change this. So this would be 19.395. And this would be 20.505. There we go. Sorry about that. Sorry about the confusion. But anyways, here it is. This is how you would do this question. Okay. The rest I will just scan and post. All right. Have a good one.